Part 3, Geometric Series. Geometric sum of a finite number of terms. Consider the geometric sequence with first term a sub 1, a common ratio r, where r is not equal to 1. The sum of the first n terms, so s sub n equals a sub 1 plus a sub 1 times r, etc., equals a sub 1 times 1 minus r to the n over 1 minus r. So if I need to find the sum of the first n terms of a geometric sequence, this is the formula that I will use. So let's find the sum of this series. I have negative 2 plus negative 6 plus negative 18 plus all the way to negative 486. So what do I need to use this equation? I need a sub 1, which I have that. It's negative 2. I need r. R here is 3 because I keep multiplying by 3, right? Negative 2 times 3 is negative 6. Negative 6 times 3 is negative 18, etc. I also need to know n. So I need to know what term number negative 486 is. So to do that, I'm going to think about what the equation for an arithmetic sequence looks like for the nth term of an arithmetic sequence. So I know that negative 486 is my nth term, which will be the first term times the common ratio to the n minus 1. If I divide both sides of this by negative 2, I will get 243 equals 3 to the n minus 1. So I need to solve this exponential equation. 243, though, is 3 to the 5th power. So I have 3 to the 5th equals 3 to the n minus 1. So 5 equals n minus 1, and n equals 6. So now I have everything I need to use that formula. So the sum of the first 6 terms is the first term, a sub 1, times 1 minus r to the n, so 3 to the 6th, all over 1 minus r, so 1 minus 3. Simplifying, I get negative 2 times 1 minus 3 to the 6th over negative 2. The negative 2's cancel, and I have 1 minus 3 to the 6th. Put that in your calculator, and you would get negative 728. If we have an infinite number of terms, like this one right here, I have 1/2 plus 1/4 plus 1/8 plus 1/16. I could keep adding terms. So here my first term is 1/2. My common ratio is also 1/2. And if I keep adding an infinite number of terms, so I just keep adding forever, what's going to happen? If I look at this square, the whole square with the dashed line and everything, that area of that square is 1. So if I take half of that area, I get 1/2. So that's my first term, is that part in blue there. Then if I take half of what's left, I have 1/4. So that part in green is the 1/4 of the total area, which is my second term. And half of what's left now, I have 1/8. So 1/8 is the next term. Half of what's left is 1/16. And I could keep doing this forever. And if I keep going and adding these terms, the sum is going to be 1 because the area of that entire square is 1. And I could keep cutting what's left in half, smaller and smaller sections. I keep adding these smaller and smaller numbers, but the whole area equals 1. So sometimes if we have a geometric series, we can find an infinite sum and actually get a number. So when does that work? This only works if our common ratio is between negative 1 and 1. Another way to write that is the absolute value of r is less than 1. Not equal to, but just less than. So between negative 1 and 1. Then we have an infinite geometric series that we can find the sum. And this formula would be the first term divided by 1 minus r. Pretty simple formula. So for example, if I want to find the value of this series, I have negative 3/4 plus 9/16 minus 27/64, etc. So my first term is negative 3/4, and the common ratio is negative 3/4. And I got that because negative 27/64 divided by 9/16 is negative 3/4. And 9/16 divided by negative 3/4 is negative 3/4. I keep multiplying by negative 3/4 to get the next term. So to find this infinite sum, I have the first term, negative 3/4, over 1 minus the common ratio. Now this only works because my common ratio is between negative 1 and 1. Otherwise, this formula would give you nonsense, something that doesn't mean anything. You'd get a number, but it wouldn't be helpful. This only works if the common ratio is between negative 1 and 1. So simplifying, I have negative 3/4 over 7/4. The 4's cancel, and I get negative 3 over 7. So the sum of this series would be negative 3/7. Let's find the value of this series if it exists. I have 2/3 plus 1 plus 3/2, etc. So my first term a sub 1 is 2/3. The common ratio, though, is 3/2, which is not between -1 and 1. 3/2 is 1.5. That's bigger than 1. So the value of this infinite series doesn't exist. I could keep adding numbers, but I'm just going to get a bigger and bigger number. I'm not going to approach any one value as I keep adding more terms. Another use of an arithmetic series is to write a repeating decimal as a fraction of integers. So if I want to write 1.13 repeating as a fraction, here's how I can use an infinite geometric series to do that. Notice that 1.13 repeating, that is 1.13, etc. That 13 will keep repeating. I could write that as 1 plus 0.13, etc., which I could write as 1 plus 0.13 plus 0.0013 plus 0.000013, and I could keep using the same pattern. I'm doing 1, 3, and then I'm adding to that this 1, 3, and then this 1, 3, and then this 1, 3, etc. So this part, not the 1, but this part right here is an infinite geometric series where the common ratio is 1/100. So the common ratio is definitely between -1 and 1. So my first term is 0.13, and my common ratio is 0.01. So if I want to write this as a fraction of integers, so I'm going to write these as fractions actually, and I get 13/100 and 1/100. So I have this 1 in front. I need that. I have 1 plus the sum. So the sum would be 13/100 divided by 1 minus 1/100, which would be 1 plus 13/100 divided by 99/100. These 100s cancel, and I get 1 plus 13/99, or 99/99 plus 13/99, which is 112/99. So you can use this idea of an arithmetic sequence, or arithmetic series, where the common ratio is less than 1 to write a repeating decimal as a fraction.